Hey everyone, welcome back. Today, we're diving into something that can feel a bit tricky, but is absolutely essential if you want to master optics: spherical mirrors. We're going to break down all the core rules so you can confidently figure out how and where an image will form every single time. So it really all comes down to one big question. If you put an object in front of a mirror, where is its image going to pop up? And how in the world do you figure out its sign? That is the core puzzle we're going to solve together today, step by step. Okay, let's get right into it. Before we can even think about drawing diagrams or solving problems, we have to learn to speak the language of mirrors. This is called the sign convention, and trust me, it's the foundation for everything else. Think of it like the grammar of optics. You gotta know it. So where does it all start? With one single point. Every single measurement we're going to take, from where the object is to where the focus is, starts right here at the pole, which we label P. Just think of it as the origin, the 0, point on our entire optical map. The good news is we can boil this whole thing down to just two golden rules. First, we'll talk about horizontal distances, so left and right, which are always measured along that main center line, the principal axis. And second, we'll look at vertical distances, or heights, measured up or down from that axis. Okay, for anything moving left or right, it's all about the direction the light is coming from. We always assume the light rays are traveling from left to right. So any distance you measure in that same direction is positive, but any distance you measure against the light, so back to the left, is negative. This is why an object's distance is almost always negative, because it's in front of the mirror and you measure from the pole back to it. Now, the vertical rule is even easier. It's just like the y-axis on a graph in math class. Any height you measure above the principal axis is positive. Anything you measure below it is negative. Simple as that. And this is the rule that tells you if an image is going to be upright or flipped upside down. All right, now that we know the rules of the road, our sign convention, it's time to grab our toolkit. To actually see and find where an image is going to form, physicists use a few special, totally predictable light rays. This is how we're going to draw some really accurate diagrams. Turns out there are 4 main power rays that are incredibly helpful. And what's really cool is you don't even need all 4. Most of the time, just picking 2 of them will let you pinpoint the exact location of any image. Let's take a look at each one. First up, we've got the parallel ray, and this one's a big deal. Any ray of light that comes in traveling parallel to the principal axes will hit the mirror and bounce off directly through the focal point F. I mean, this rule is literally what defines the focal point. Rule number 2, the focal ray, is basically the total opposite of the first rule. It really shows how light is reversible. If a ray first passes through the focal point before it hits the mirror, it will bounce off and travel out perfectly parallel to the principal axis. See? These first 2 rules are like a perfect reverse pair. Super handy. Now, the center ray, this one's special. Any ray that passes through the center of curvature, C, hits the mirror dead on at a 90-degree angle, and what happens then? It reflects straight back along the exact same path it came from. It's like throwing a ball perfectly straight at a wall. It comes right back at you. And last but not least, the pole ray. When a ray hits the mirror right at the pole, P, the principal axis itself basically becomes our normal line, so it's a perfect showcase of the law of reflection. The angle it comes in at is the exact same angle it leaves at, making this neat, symmetrical V-shape. Okay, drawing these rays is awesome for getting a feel for things, right? But if we want to be super precise, we need to bring in the math. So now let's unlock the secret code of spherical mirrors, the formulas that really run the whole show. The first relationship is super simple but really important. For the rays we usually work with, the ones close to the principal axis, the focal length, little f, is exactly half of the mirror's radius of curvature, big R. This little formula, f equals r over 2, is a lifesaver. It tells us the focus is always perfectly halfway between the pole and the center of curvature. And now for the main event, the mirror formula. This one beautiful equation connects everything: the object distance u, the image distance v, and the focal length f. If you know any 2 of these, you can always find the third. This is your go-to equation for pretty much any calculation you'll need to do. Now, pay close attention to this table because it's absolutely crucial. It connects our sign convention directly to that formula we just saw. So for a real object, u is negative. If a real image forms where the light rays actually cross, then v is also negative. But if you get a virtual image, one that seems to be behind the mirror, then v will be positive. Think of this as your ultimate cheat sheet for getting the signs right every single time. All right, so we've got the theory down, we know how to draw the diagrams, and we have the formulas. So how do we put it all together to absolutely crush it on an exam? Let's talk strategy. First things first, let's talk about the common mistakes so you can avoid them. The number one error is forgetting to apply the sign convention when you plug numbers into the formula. Another big one is mixing up focal lengths. Just remember, a concave mirror that converges light has a negative f, but a convex mirror that diverges light has a positive f. And of course, always double check your math and try to draw neat diagrams. Avoiding these traps is half the battle won. So you're in the exam and you see this question. They're asking you to just state the sign convention. This is your cue to clearly lay out the rules we just covered. The pole is the origin, distances along the light are positive, against are negative, and heights above the axis are positive, below are negative. And here's another one you're almost guaranteed to see. State the 4-ray rules. You need to be ready to clearly describe the parallel ray, the focal ray, the center ray, and the pole ray. Knowing these by heart is key for both theory marks and for actually drawing diagrams that get you the right answer. So listen, if there's one thing you take away from all this, let it be this. The sign convention is the master key that unlocks everything else in mirrors. Once you understand it properly, you can solve any numerical question they throw at you. Once you have a rock-solid grip on these rules, everything else, the diagrams, the formulas, even the hardest problems, just falls into place. Master the signs, and you'll master spherical mirrors.